Alright, section 2.4, limit properties. Time has almost come for us to actually compute some limits. However, before we can do that, we'll need some properties of limits that will make our lives somewhat easier. So let's take a look at those first. The proof of some of these properties can be found in the proof of various limit properties section of the extras chapter. Okay. Properties. First, we will assume that the limit of f of x is x pertus a, the limit of g of x is x pertus a exists, and that c is any constant. Then, the limit of c, a constant, times f of x is x pertus a equals, so you can put it out front. In other words, we can factor a multiplicative constant out of a limit. So to take the limit of a sum or difference, all we need to do is take the limit of the individual parts and put them back together with the appropriate sign. This is also not limited to two functions. This fact will work no matter how many functions we got separated by plus or minus. Okay. The limit of f of x times g of x, yeah, you can split them up. We take the limits of products in the same way that we can take the limit of sums or differences. Just take the limit of the pieces and then put them back together. Also, as with the sums, as with sums or differences, this fact will work no matter how many functions we've got separated by plus or minus. Wait, I think I already read that one. Also, as with sums or differences, this fact is not limited to just two functions. Alright. This one you divide. You can divide them, unless the denominator is 0. As noted in the statement, and we only need to worry about the limit and the denominator being 0 when we do the limit of a quotient. If it were 0, we would end up with a division by 0 error, and we need to avoid that. And then the other one, you can put the exponent on the outside. For where n is any real number. So in this property, n can be any real number, positive, negative, integer, fraction, irrational, 0, etc. In the case that n is an integer, this rule can be thought of as an extended case of 3. For example, consider the case of n equals 2. Yeah, you can do that, sure. The same can be done for any integer n. Okay. This is just a special case in the previous example. Okay. The limit of a constant is always the constant. And the limit of x is x pertus a is always a. And the last one, special case of property 5. Yeah, okay. Note that all of these properties also hold for the two one-sided limits as well when we just didn't write them down with one-sided limits to save on space. Let's compute a limit or two using these properties. The next couple of examples will lead us to some truly useful facts about limits that we will use on a continual basis. Alright, example 1. Gotta restart this. compute the following limit. Okay. We got 3x squared plus 5x minus 9. Alright. So split this up by addition first, I guess. And then, nah, it's gotta be negative right here. And then split them up by multiplication. X squared plus the limit of x approaches to 5 times, I'll put these in parentheses, minus, this is just 9. This is 3 times, we can put this on the outside like this, which would be 2 squared plus 5 times 2 minus 9. This, I already did, like, plug 2 in my head. This should be -7. So if I don't get -7, it's wrong. I think we're good though. Plus 10 minus 9. 12 plus, wait. No, this should be negative. Alright, well, let's see. 3x squared plus 5, or wait, did I just plug it in wrong? Try it again. 4, 12. Oh wait, it's not -7. $13. Guess I plugged it in wrong. Should be right. Three plus, yeah, 13. Okay. I think we're good then. That's the annoying way of doing it with the properties. This first time through, we will use only the properties above the compute the limit. First, we will use property 2 to break up the limit into 3 separate limits. We'll then use property 1 to bring the constants out of the first 2 limits. Doing this gives us okay. I don't think Professor Leonard went over property 2. Or it's useless anyway. Property 7 and 9. Yeah, okay. Wait, -7? Oh, it's a -2, that's why. That's why I got -7 the first time. This x approaches -2, that's it. So this should be -2. This is 5. This is a -2. 12 minus 10. That's why that should have been negative. 12 minus 10 minus 9. Now let's notice that if we had defined, yeah, if you just plugged in -2, you get the same thing. In other words, in this case, we can see that the limit is the same value that we get by just evaluating the function at the point in question. This seems to violate one of the main concepts about limits that we've seen to this point. In the previous 2 sections, we made a big deal about the fact that limits do not care about what is happening at the point in question. They only care about what is happening around the point. So how does the previous example fit into this, since it appears to violate the main idea about limits? Despite appearances, the limit still doesn't care about what the function is doing at x equals -2. In this case, the function that we've got is simply nice enough so that what is happening around the point is exactly the same as what is happening at the point. Eventually, we will formalize up just what is meant by nice enough. At this point, let's not worry too much about what nice enough is. Let's just take advantage of the fact that some functions will be nice enough, whatever that means. Function in the last example was a polynomial. Turns out all polynomials are nice enough so that what is happening around the point is exactly the same as what is happening at the point. This leads to the following fact. Finding the limit of a polynomial, you could just plug in a, By the end of the section, we will generalize this out considerably to most of the functions that we'll be seeing throughout this course. Let's take a look at another example. Okay. Can I copy paste this? Wait, can I do this the whole time? Why not let me? Oh jeez. Yeah, maybe not. Doesn't copy well. Okay. Example 2. 6 minus 3z plus 10z squared over -2z to the power of 4 plus z, or 7z cubed plus 1. Finding the limit as z approaches 1. I'm just going to plug it into the denominator first, see if there's a problem. I doubt there is though. -2 plus 7 plus 1. 6, and then plug it in the top. 6 minus 3, 1 plus 10, 1 squared. 6 minus 3 plus 10, 13, 13 over 6. That's the answer. Yeah, okay. Oh, are they? They're using the properties. Alright, I don't really want to, so. First, notice that we can use property 4 to write the limit as. Well, actually, we should be a little careful. We can do that provided the limit of the denominator isn't 0. As we will see, however, it isn't in this case, so we're okay. Now, both the numerator and denominator are polynomials, so we can use the facts above to compute the limits of the numerator and the denominator, and hence the limit itself. Notice that the limit of the denominator wasn't 0, so our use of property 4 was legitimate. In the previous example, as with polynomials, all we really did was evaluate the function at the point in question. So it appears that there is a fairly large class of functions for which this can be done. Let's generalize the fact from above a little. Provided f of x is nice enough, we have okay. Again, we will formalize up just what we mean by nice enough eventually. At this point, all we need to worry about is which functions are nice enough. Some functions are nice enough for all x, while others will only be nice enough for certain values of x. It will all depend on the function. As noted in the statement, this fact holds for the two one-sided limits as well as the normal limit. Here's a list of some more common functions that are nice enough. Polynomials are nice enough for all x's. If f of x equals p of x over q of x, then f of x will be nice enough, provided p of x and q of x are nice enough, and if we don't get division by 0 at this point, at the point we're evaluating it. Cos x, sin x are nice enough for all x's. Secant x, tan x are nice enough provided that x does not equal okay, in other words, secant and tangent are nice enough everywhere cosine isn't 0. To see why, we recall that these are both really rational functions and that cosine is the denominator of both. Then go back up and look at the second, wait, what? To see why, recall that these are both really rational functions and that cosine is in the denominator of both. And go back up and look at the second bullet above. Okay, I don't know. It's weird. Cosecant, cotangent are nice enough provided x does not equal those. In other words, cosecant and cotangent are nice everywhere sine isn't equal to 0. N square roots of x is nice enough for all x if n is odd. N squared of x is nice enough for x is greater than or equal to 0 if n is even. Here we require that x is greater than or equal to 0 to avoid having to deal with complex values. A to the power of x, e to the power of x are nice enough for all x's. Log b of x, natural log of x are nice enough for x is greater than 0. Remember that we can only plug in positive numbers into logarithms and not 0 or negative numbers. Any sum, difference, or product of the above functions will also be nice enough. Quotients will be nice enough provided that we don't get division by 0 upon evaluating the limit. The last bullet is important. This means that for any combination of these functions, all we need to do is evaluate the function at the point in question, making sure that none of the restrictions are violated. This means that we can do a large number of limits. Evaluate this. Okay. Negative 5 square roots of x plus e to the power of 3. What is this thing? 1 plus the natural log of 3 plus sine 3 cos 3. It's gonna be hard to plug in, dude. So we got negative, wait, how do I type this in? How to put a number in front of square root. Wait, that's not what I want. It's negative 2. Oh wait, that's not how you say this. 5 roots of 3. That's not what I want. Cube root of 5 or 5th root. Okay, 5th root. How to type in 5th root. Here we go.
To work out the 5th root of a number using a Casio ClassWiz scientific calculator. Locate the root key, which is on the 2nd row of the scientific function.
It's a different calculator though. Yeah, you know I don't have this one.
Welcome to my channel. I have a calculator of Casio.
It's a different calculator too.
Hello everyone, this is just going to be a quick tutorial on how to calculate cube roots on the TI-84 plus CE or any other TI-84. So starting from the home screen, all you have to do is press Math and then scroll down to the 4th option.
Oh, there it is.
Cube root.
Wait, that's cube, no!
And you can now find the cube root.
Can you change it? Maybe you can change it. Oh, there's an X right here. Can I like... No, man. Math. Try that again. No, okay. Maybe I can change the 3 then. Man, how do you do this?
Of any number. So for example, the cube root of 8 is 2. And as you can see here, there is another option that has the root of x. So for this you can find the root...
Wait, how is he able to type it in though?
That has the root of x. So for this you can find the root, the nth root of any number. So if you want to find the 5th root...
Dude, he gets to type it in. That's so stupid. Answer.
Okay, I'm going to show you how to take a root of a number that's higher than a square root or a cube root. So let's say we're going to take the fifth root of 3,125. So we're going to turn on the calculator, and we're going to type the number 5 because we're going to take the fifth root. And then we press math, and we go to...
Oh, you type in the number you want to do first, really? Is that really how it works?
Number 5, which shows an x root of a number, so we press 5.
What? Bruh. Mine did not do that. Dude.
So it gives me the fifth root of some
Mine's
number,
bugged.
and I just need to type the number in there. We're going to put 3,001.
How to type higher roots on... Wait, is this a TI-83?
In this video, we're going to take a look at using the TI-83 Plus and the TI-84 families of calculators to calculate higher order radicals. Now the trick here is, in previous videos, I mentioned how to do squares and cube roots, and it's usually you just press a button or two and then you enter the number. When you're dealing with fourth order and higher radicals, you need to put the index in first. And I recommend doing all of this in parentheses so you don't get confused as to what's happening before or after. So to start with, I'm going to go ahead and insert a set of parentheses. I type in the index first. Recall that the index is this little number out front. I have to identify the index first, and so that's 4. Then I press my math key, and option number 5 is called the
Oh,
X
he's doing the same
root.
thing.
And the Xth root is going to look at immediately in front of it for the number or the index of the root. And so I can scroll down and press enter, or I can just select 5 and it'll boot me back to the home screen.
Really? So it still does
And
that.
so what I'm saying is take the fourth root of, and now I have to, and I would say in parentheses again, put in my radicand.
Okay. That's really dumb, but... Did I not plug in my number? Or no, I did, just not for this one. For some reason. 3. Then another parenthesis. Alright, plus. E. Where's E? Are you serious? Alright, next problem.
Just look, I say number
How to type an E on the TI-83.
In this video, I'd like 100 e to the 0 and so on. Let's say we can just do 0.04 to our model.
I just want to see
Now
how
we
to
can use
type it in, bruh.
on the calculator, we're going to need to use the ln.
There we go, okay. Wait a minute. Okay. Like that. Divided by 1 plus natural log of 3 plus sine 3 times cos 3. I swear, if it gives me an error. Okay. Don't know if that's right. 0.676. 9. Are you serious, dude? Man. so annoying to type in. This isn't even fair. Wait, did I not put a negative in front? I didn't put a negative. Okay. Try it again, I guess. Wait a minute, I didn't put a 5 yet, did I? E to the power of 3 divided by 1, in parentheses, 1 plus natural log 3 plus sine 3 cos 3. Are you serious, dude? What am I doing wrong? This is so dumb. Dude, I'm getting a different answer every single time. What is going on? I'll type this in the like math way or something. Okay, now I get it. Or wait. I'm still off? Are you kidding? What? Wait, why did it do this to the fraction? Well, that shouldn't matter though. e cubed 1 plus natural log 3 sine 3 cos. I don't know, man. Like, that's actually crazy. So it should be 8.1854, I guess. Okay. Section 2.5, computing limits. In the previous section, we saw that there is a large class of functions that allow us to use that to compute limits. However, there are also many limits for which this won't work easily. The purpose of this section is to develop techniques for dealing with some of these limits that will not allow us to use just this fact. Let's first go back and take a look at one of the first limits that we looked at and compute its exact value and verify our guess for the limit. Okay, so you get a 0 on the bottom. You get a 0 on the top. Yep. Okay, so you can factor it. X plus wait. X plus 6, X minus 2. Then X minus 2. There, let's cancel out. It's plus 6 over X. X over X plus 6 over X. 1 plus 6 over X. Or wait. Once you have this form, you can just plug it in. 8 over 2. Oh, you gotta keep putting that limit, I forgot. And then here you don't need a limit, this is 4. First, let's notice that if we try to plug x equals 2, we get undefined. So we can't just plug in x equals 2 to evaluate the limit, so we're going to have to do something else. The first thing that we should always do when evaluating limits is to simplify the function as much as possible. In this case, that means factoring both the numerator and the denominator. Doing this gives, So upon factoring, we saw that we could cancel an x minus 2 from both the numerator and the denominator. Upon doing this, we now have a new rational expression that we can plug x equals 2 into because we lost the division by 0 problem. Therefore, the limit is 4. Note that this is, in fact, what we guessed the limit to be. Before leaving this example, let's discuss the fact that we couldn't plug x equals 2 into our original limit, but once we did the simplification, we just plugged in x equals 2 to get the answer. At first glance, this may appear to be a contradiction. In the original limit, we couldn't plug in x equals 2 because that gave us 0, 0. The 0, 0 situation that we couldn't do anything with. Upon doing the simplification, we could get, In other words, the two equations give identical values except that x equals 2, because limits are only concerned with what is going on around the point x equals 2. The limit of the two equations will be equal. More importantly, in the simplified version, we get a nice enough equation. And so what is happening around x equals 2 is identical to what is happening at x equals 2. We can therefore take the limit of the simplified version simply by plugging in x equals 2, even though we couldn't plug x equals 2 into the original equation, and the value of the limit of the simplified equation will be the same as the limit of the original equation. On a side note, the 0 over 0 we initially got in the previous example is called an indeterminate form. This means that we don't really know what it will be until we do some more work. Typically 0 in the denominator means it's undefined, however that will only be true if the numerator isn't also 0. Also 0 in the numerator usually means that the fraction is 0 unless the denominator is also 0. Likewise, anything divided by itself is 1 unless we're talking about 0. So there are really 3 competing rules here. It's not clear which one will win out. It's also possible that none of them will win out, and we will get something totally different from undefined 0 or 1. We might, for instance, get a value of 4 out of this, to pick a number completely at random. When simply evaluating an equation, 0 over 0 is undefined, however, in taking the limit, if we get 0 over 0, we can get a variety of answers, and the only way to know which one is correct is to actually compute the limit. There are many more kinds of indeterminate forms, and we will be discussing intermediate indeterminate forms at length in the next chapter. Let's take a look at a couple more examples. Jeez, okay. So we got example 2, the limit of 2 times negative 3 plus h minus 18 for h is x, or as h approaches 0. Alright, this is a whole. Should be able to factor an h out, right? Ah, the 18s cancel out. Look at that. It's crazy, dude. And I'll get a new page. So you can factor the h out of them. Cancel out the h's. And -12. In this case, we also get 0 over 0, and factoring is not really an option. However, there's still some simplification that we can do. So upon multiplying out the first term, we get a little cancellation, and now notice that we can factor out an h out of both terms in the numerator, which will cancel against the h in the denominator, and the division by 0 problem goes away, and we can evaluate the limit. Alright, next one. Okay. You can factor this. Forget t minus 4 somehow. Conjugate maybe? Okay. Yeah, this definitely isn't what you want to do. multiply by the conjugate at the top, maybe? Wait, this should be negative. Or wait, it can't be. Wait. That should be a distribute the negative. Alright, I think it's 5/8. Wait, negative 5/8. What? Oh, we'll see. This limit is going to be a little more work than the previous two. Once again, however, note that we get the indeterminate form 0 over 0 if we try to just evaluate the limit. Also note that neither of the two examples will be of any help here, at least initially. You can't factor the equation, and we can't just multiply something out to get the equation to simplify. When there's a square root in the numerator or denominator, we can try to rationalize and see if that helps. Recall that rationalizing makes the use of the fact that, okay. So if either the first and or second term square root in them, the rationalizing will eliminate the roots. This might help evaluating the limit. Let's try rationalizing. Oh, multiplying by the conjugate. Remember that to rationalize, we just take the numerator, change the sign, multiply. Next we multiply the numerator. Careful to watch the minus signs, which is probably where I messed up. T squared minus 3t plus 4. No, I did distribute that. Then 4 minus t plus square root of 3t plus 4. Okay. Notice that we didn't multiply the denominator out as well. Most students come out of an algebra class having it beaten into their heads to always multiply this stuff out first. However, in this case, multiplying out will make the problem very difficult, and in the end, you'll just end up factoring it back out anyway. At this stage, we're almost done. And we can factor t minus 4 t plus 1. T minus 4 t plus square root of 3t plus 4. Alright, good so far. Did I plug in the 4 wrong? Are you kidding? Now all we need to do is notice that if we factor out a -1 in the first term in the denominator, we can do some canceling. Oh, it's 4 minus t. You can't. Oh, crap. Okay. So that has to be factored out before you can swap it. Oh, wait. So that leaves a negative here. Ah, okay. If we had multiplied the denominator out, we would not have been able to do this canceling, and in all likelihood, we would not have even seen that some canceling could have been done. So we've taken a look at a couple of limits in which evaluation gave the indeterminate form 0 over 0, and now we have a couple things to try in these cases. Let's take a look at another kind of example that can, another kind of problem that can arise in computing some limits involving piecewise functions. Okay. Compute the limit of g of y as y approaches 6. So first one is 6. One minus 3, 6. 1 minus to negative 17. I don't see a problem so far. Negative 2. The limit of g of y. Y approaches negative 2. 1 minus 3, negative 2. 1 plus 6. In this case, really isn't a whole lot to do. In doing limits, recall that we must always look at what's happening on both sides of the point in question as we move towards it. In this case, y equals 6 is completely inside the second interval for the function, so there are values of y on both sides of y equals 6 that are also inside this interval. This means that we can just use the fact to evaluate this limit. Okay. So for this one, if it's less than -2, that's something completely different. I don't know how you'd show that though. This part is the real point to this problem. In this case, the point that we want to take the limit of is the cutoff point for the two intervals. In other words, we can't just plug y equals -2 in the second portion because this interval does not contain values of y to the left of y equals -2. And we need to know what is happening on both sides of the point. To do this, we are going to have to remember the fact that from the section on one-sided limits, that says if the two one-sided limits exist and are the same, then the normal limit will also exist and have the same value. Notice that both of the one-sided limits can be done here, since we are going to be looking at one side of the point in question. So let's do the two one-sided limits, see what we get. Okay. That's how you prove it then. So this would be from the right. Y squared plus 5. Nine. Note that a very simple change to the function will make the limit at y equals -2 exist, so don't get into your head that limits at these cutoff points in piecewise functions don't ever exist, as the following example will show. Y squared plus 5 if y is less than -2. 3 minus 3y if y is greater than or equal to -2. Okay. Yep, they're the same. The two one-sided limits this time are those. The one-sided limits are the same, so yeah, okay. There's one more limit we need to do, however, we will need a new fact about limits that will help us to do this. If f of x is less than or equal to g of x for all x on AB, except possibly at x equals c, and the constant is between a and b, then alright, that's kind of confusing, but note that this fact should make some sense to you if we assume that both functions are nice enough. If both functions are nice enough to use the limit evaluation fact that we have, the inequality is true because we know that c is somewhere between a and b. In that range, we also know f of x is less than g of x. Note that we don't really need the two functions to be nice enough for the fact to be true, but it does provide a nice way to give a quick justification for that fact. Also note that we assume that f of x is less than or equal to g of x for all x on AB, except possibly at x equals c, because limits do not care what is actually happening at x equals c. We don't really need the inequality to hold at a specific point. We only need it to hold around x equals c, since that is what the limit is concerned about. You can take this fact one step further to get the following theorem, the squeeze theorem. Suppose that for all x on AB, same thing again, we have that. Okay, and suppose that the limit to the same value. Yeah, okay. As with the previous facts, we only need to know that h of x is between f of x and g of x when x equals a constant, because we are working with limits and they are only concerned with what is going on around the constant and not what is happening at the constant. Now if we again assume that all three functions are nice enough, it's not required to make the squeeze theorem true, helps with the visualization, we can get a quick sketch of what the squeeze theorem is telling us. Okay. From the figure we can see that the limits of f of x and g of x are equal at x equals c. So the function must also be equal to x equals c. Therefore the limit of h of x at this point must also be the same. It's also known as the sandwich theorem and the pinching theorem. Interesting. So how do we use this theorem to help us with limits? Let's take a look at the next example. We got cos, okay. The limit of x squared cos of 1 over x as x approaches 0. Okay. This example, none of the previous examples can help us. There's no factoring or simplifying to do. We can't rationalize, and one-sided limits don't work. There's even a question as to whether this limit will exist since we have division by 0. The first thing to notice is that the following fact about cosine is between -1 and 1. Our function doesn't just have an x in the cosine, but as long as we avoid x equals 0, we can say the same thing for our cosine. Okay. It's okay to ignore x equals 0 because we're taking a limit. We don't care what's going on at the points. Multiply everything by an x squared. In other words, we managed to squeeze the function that we were interested in between two other functions that are easy to deal with. Oh, okay, I see how this works again. Kind of forgot. So if you plug 0 in, then you know it has to be 0. Okay. And there's the graph. Okay. In this section we've seen several tools we can use to help us compute limits, in which we can't just evaluate the function at the point in question. So we'll see many of the limits that we'll be doing in later sections require one or more of these tools. It's the next section. Infinite limits. Did I go over that in the video yet? I don't think I did, actually. Well, no I didn't, but I don't think Professor Leonard goes over it either, so. Oh wait, vertical asymptotes, okay. So I'll do these 3 next. Then watch the next video, continuity. Watch the next one, okay, that's what I'm doing. How long are these ones? 7 examples, really? Okay. That's it for the day.